Okay, good afternoon. We are going to start on three-phase induction motor drives today. We had already seen various power converter topologies like AC to DC, DC to DC, DC to AC, and so on. And we had also taken a look at how to apply, for example, a DC to DC converter to control the speed and torque of a DC motor. So DC to AC inverters are primarily used in the control of induction motors and synchronous motors. So let us first of all start with induction motor, three-phase induction motor. Three-phase induction motors, if you look at it, 80% of the industrial drives that are used are generally three-phase induction motors. This is because of several advantages of three-phase induction motor. If you just give a three-phase supply and switch it on, the induction motor will start on its own. So the first and foremost advantage is it is a self-starting motor. You don't have to have a separate starting mechanism. In fact, a DC motor is also a self-starting motor. If you switch on the field and armature supplies, basically the DC motor starts on its own. Induction motor is also a self-starting motor, but some of the other motors, for example, like a single-phase induction motor or a synchronous motor, they are not self-starting. You have to make special starting arrangement. That is one thing. Second thing is, if you look at a single-phase induction motor or any other AC motor, if we say this is the voltage that is being applied to the motor, the current will lag behind by certain angle because it is inductive in nature. So we are going to have the current somewhat like this. What is being carried by the motor will be somewhat like this. So if we are looking at the product of voltage and current, which is the power. So let us say this is the voltage and this is the current. So if we look at the power, we are going to see that voltage is positive here, but until this point, the current is negative. So if I look at VI, which is the instantaneous power, the product of V and I, we are going to have a positive quantity, negative quantity during this portion. Then it will be positive until this portion. So this is going to be the kind of power we have. And again, we are going to have a negative quantity during this portion. And from here to here, it is going to be positive. So this is the way the power is going to be. So the power what we get, the instantaneous power is oscillatory. So instantaneous power, if it is oscillatory, then we can say the power which is a product of torque and omega. The torque is going to be oscillatory because the speed will vary only as per the inertia. If the inertia of the drive is fairly large, the speed will not have as many oscillations like the power has. So you are going to see the oscillations generally in the torque. So if we are going to have oscillations in the torque, in that case, you will see vibrations in the shaft. So we are going to generally see vibrations in the shaft. That is the reason why generally single phase motors are hardly ever used beyond 1 kilowatt capacity. So if you look at single phase motors, generally they are used in applications only less than 1 kilowatt capacity. Whereas if you look at three phase, all the three phase power when you add together, so this may be for one phase, which is oscillatory. Another phase will also be oscillatory, but it will be having the negative portions in some other point. The same way the third phase will have again negative portions at some other point. So the summation of all three powers in the three phase case, that will be a steady value. So the torque and power output are generally steady. Okay, they are steady. So you are hardly going to see any vibration. In fact, this brilliant discovery was made by Tesla that if you use three-phase, you are going to have normally the power and torque to be a steady value. So this brilliant discovery was made by Tesla, and that is the reason why three-phase motors have come into existence and they have been working for several years now. Another thing is the three-phase motors generally are going to be maintenance free, especially the squirrel cage induction motor, what we are going to talk about eventually. Those are maintenance free as compared to DC motor as well as synchronous motor. So we are talking specifically about squirrel cage induction motor. So this is used in many of the application like many industrial drives, traction drives for suburban train system. Many of them are working with induction motor because of the fact that you can employ them, you can put them in service and forget about it for several decades. So these are the major advantages, and that is one reason why induction motors are very commonly used as industrial drives. There are definitely demerits also for induction motor drive. First and foremost thing is because it is going to have the magnetizing current as well as the torque producing component of current. So magnetizing current is very similar to the field current in a DC motor. So we are going to have a current which produces flux in the air gap between the stator and rotor. So this is very similar to the field current of the DC motor. And the other current, which is actually the rotor current, that is going to be equivalent to the torque producing component of current or armature current of a DC motor. So both are together carried by the stator. So the stator current actually consists of two portions. One is the reflection of rotor current and the other one is going to be the magnetizing current. So that is the reason why the power factor of this induction motor will always be lagging. So power factor can never be unity. It can be only lagging. So magnetizing current is equivalent to the inductive portion of the current. That is the reason why we have lagging power factor. And because it is lagging power factor, generally efficiency is poorer. It's not going to be as good as the efficiency of synchronous machine, which has power factor adjustment possible. Power factor can be leading or lagging or unity. So efficiency is not as high as it is in synchronous machine. So this is one of the major disadvantages of induction machine. Another demerit we can say for induction motor is speed and torque control is not very easy. That is because we are going to see that very often we will not be able to access the rotor current at all. So it is difficult to access rotor current. So if we are not going to be able to access the rotor current, measure the rotor current itself, then it is almost impossible to control it. And rotor current definitely plays a very vital role in torque production. So if we are not able to control it, then it is going to be very difficult to control the torque. Another thing is the speed depends upon the frequency of the power supply. So it depends upon the frequency of the power supply given to the stator. So unless we have a chance to vary the frequency, we are not going to be able to control the speed very easily. And that is definitely pretty difficult in the case of a three-phase induction motor unless we have an inverter. If we have a DC to AC converter, it will be able to control. So this is the inverter is the only thing which can control the frequency or vary the frequency, adjust the frequency as per our requirement, which will actually allow the speed control. So DC motor, the speed control becomes much simpler. It can be done just by armature voltage control. It can be just done by controlling the field current value, but you cannot do that in the case of an induction motor. So it becomes much more difficult in the case of induction motor. And another thing is the starting torque normally is not very high. The starting torque is going to be low, whereas the starting current will be quite high. So if we are starting multiple induction motors simultaneously, if I say that I have 5 or 6 induction motors in my industrial premises and I'm going to start all of them together. So simultaneous starting of multiple induction motor generally is going to make a voltage dip because the current will increase tremendously. So it will cause voltage dip. So you may have a sinusoidal voltage normally like this from the power system. So let us say this is the kind of magnitude you are having. And when we start the induction motor, suddenly the voltage can dip tremendously. So this can really lead to something called voltage sag. So voltage sag is a common problem we may encounter when we start multiple induction motors. So, for example, an electric vehicle application, it will always require a large starting torque because electric vehicle itself is going to be pretty heavy. So, to make it rolling, make the wheels rolling, you will require a very high starting torque, and that may not be possible. You may not be able to really develop a large starting torque in the case of a three-phase induction motor. So these are some of the problems that could be faced when you use a three-phase induction motor in your industrial premises. Okay, so now let us first of all try to understand the basic construction and principle of operation. Construction and principle of operation of a three-phase induction motor. So we are going to look at both the basic construction as well as principle of operation of a three-phase induction motor. Okay, so a three-phase induction motor consists of distributed winding in the stator. So it is going to have a distributed winding in the stator. So what is going to happen is if this is my stator cross section and this is going to be the outer cylinder and the rotor is going to be the inner cylinder. So in the inner cylinder, if this is the rotor, you may have slots carved at the outer periphery of the cylinder. So this is how the slots are carved in the outer periphery of this rotor. Okay. And we are going to have, as far as the stator is concerned, in the inner periphery, we are going to have the slots carved out like this. So this is the way generally the slots are going to be constructed in the entire induction motor stator. Now, we are going to have the three-phase winding distributed along this. So maybe I will have A-phase winding here, and I will have the return path for A-phase like this. So let me call this as dot. So this is dot, and this is going to be cross. The currents are going to be cross. So you can imagine that the conductor is going like this, and it is going to turn around like this, and it will come through this cross like this. So like this, you are going to have the turns. We have shown here 2 turns of A phase. So let us say this is A and this is going to be A dash, which is the return path. Similarly, I'm going to have B phase, which is about 120 degrees shifted from original A phase. And I'm going to have the B phase winding coming up here like this. So this is going to be cross and this is going to be dot. And as far as the C phase is concerned, I'm going to have again C phase winding sitting here, which is again 120 degrees away from B phase. And I'm going to have the opposite side. I'm going to have the cross of C phase. So this is C dash and this is going to be C. And this is going to be B and this is going to be B dash. So A phase, B phase and C phase windings are distributed and they are arranged in space shifted manner within this inner periphery of the stator itself, the stator slot itself. So the stator has phase distributed winding. And the rotor is going to have also three-phase winding. Rotor will also have three-phase winding. If it is a wound rotor. So there are two kinds of rotor. One is called wound rotor or slip ring rotor. This is one of the types of rotor. And the other type of rotor is called squirrel cage rotor. So squirrel cage rotor will have rotor conductors which are arranged in the form of something like a cage. So I'm going to have an end ring, and then from the end ring, I'm going to have the conductors, connected like this. So this is the rotor conductor. So I'm going to have this short circuited with another end ring here. So I'm going to have two end rings in the two ends of the rotor, and it is going to be arranged in the form of a cage. So something like this, you can see that this is what is the squirrel cage construction, where you are going to have this thick conductors, which are the rotor bars, and in the two ends, they are going to be short circuited with end ring. If it is a wound rotor will basically have conductors, three-phase conductors, exactly similar to what we had in the case of stator. And those conductors, ultimately, the ends of those conductors are going to be brought to three rings, which are actually on the top of the shaft itself. So these are the three-phase rings. And from the three-phase rings, we are going to have brushes which are making contact with the help of some kind of spring arrangement. And from here, we are going to take out the connection externally. So if we want to draw the wound rotor kind of construction, we have to show the three-phase windings somewhat like this. These are the three-phase windings which are arranged very similar to the stator arrangement. And here is the shaft. So what is going to happen is around the shaft, I am going to have one ring, which is for A phase. I'm going to have the second ring, which is for B phase. And I'm going to have the third ring, which is for C phase. And all three of them are going to be insulated from each other because the three phase cannot be short circuited with each other. Now, from here to this particular ring, I would connect A phase conductor directly if this is A phase conductor. And from here, I will try to connect the B phase conductor directly. So this is the B phase conductor. And from here, I'm going to connect the C phase conductor like this. So this is going to be connected with C phase conductor. Okay. Now on the other side, we will have a brush which is making contact with the slip ring with the help of a spring. A spring will hold it tight and it will make contact. And from here, we are going to bring out the connection outside. And if I want to short circuit the rotor, I can short circuit it externally with the help of wire. So these are the slip rings. What I have got in black color, this is going to be slip ring. And whatever I'm showing in green color, this is going to be brush. And this, whatever I have done here is the external short circuit. So externally, this is going to be short circuited outside the machine. So in squirrel cage induction motor, so this is the squirrel cage rotor. Here, the short circuiting is done internally. So you cannot measure the rotor current. You can't bring out the rotor current. The short circuiting is done internally. So there is nothing like a moving contact in this particular case. Whereas in slip ring rotor or wound rotor, we are going to have moving contacts. So the moving contact is here. The brush and slip ring arrangement, that is basically a moving contact. So wound rotor will have access to the rotor current, whereas squirrel cage rotor will not have any access to the rotor current. So squirrel cage rotor, it is very difficult to control the rotor current. You can't even measure it, leave alone controlling it. Whereas in squirrel cage, in wound rotor, you will be able to measure the rotor current. You would be able to control it also if you want to. But because of the moving contact, this will require frequent maintenance. We have to check whether the contact is happening properly or not. So this requires continuous observation and frequent maintenance, whereas the squirrel cage rotor is completely maintenance free. So both of them have their advantages as well as disadvantages. Okay. So these are the two kinds of rotor structure that we normally see in the case of three-phase induction motor. So the basic construction is somewhat like this. The stator has three-phase space distributed winding, and the rotor has again either three-phase space distributed winding or it will be a cage rotor. So one of the kinds of arrangement it will have. Now, let us try to look at what is the kind of principle of operation the three-phase induction motor has. So what we are going to do is from the stator side. So from the stator side, a three-phase current input, time distributed, that is time-phased current, three-phase time-phased current will be given to the three-phase winding. So the stator has three-phase space distributed winding, and to them we are going to give three-phase time distributed current. So what we are seeing is we are going to have, let us say this is the stator inner periphery. I'm going to have A phase here. So this is dot and this is cross. This is the A phase winding. So with the help of thumb rule, we should be able to say A phase MMF or flux will be along this direction. So this is the A phase axis. The same way, if I'm going to have B phase winding here, this is dot and this is cross. So we are going to have the B phase winding somewhat like this. We are going to have the B phase winding at 180 degrees, 120 degrees. So this is going to be B phase axis. And we are going to have C phase axis somewhat like this. So this is going to be dot and this is going to be cross for the C phase. So we will have the C phase axis somewhat like this. So we are going to have A phase, B phase and C phase axis like this. So this is A dash return path. This is going to be B and this is B dash, B phase return path. And this is going to be C and this is C dash. This is how it is going to be. Now A phase, B phase, C phase axes are given here. So if I am going to have a sinusoidal supply for the three phase, let us say this is my A phase current. And I'm going to have B phase and C phase currents which are shifted from each other by 120 degrees. So I'm going to have the B phase current somewhat like this. And I'm going to have the C phase current somewhat like this. So this is going to be the C phase current. So if I am looking at the point where this is omega t. So let us say this is omega t equal to 30 degrees. So this is going to be omega t equal to 30 degrees. And this is going to be omega t equal to 90 degrees. And this is going to be omega t equal to 150 degrees. So let us try to look at what happens to the overall flux during these three portions. So at omega t equal to 30 degrees. So A phase axis is along this, and B phase axis is along this, and C phase axis is along this. So at omega t equal to 30, we are going to have this is A, this is B, and this is C. So C phase is 50% of the peak, because that is sine 30, let us say. So that is going to be 50% of the peak and in the positive direction. And A phase is also 50% of the peak, that is also in positive direction. So this is A, this is B, and this is C. And A phase current is in the positive direction, but that is only about 50% of magnitude. C phase current is also in the positive direction, that is also 50% of the magnitude. But at that point, if I try to look at B phase is maximum or peak, but it is in the negative direction. So I should take the B phase in this direction, and I should draw it twice the magnitude of this. So the resultant is going to be along this. So this is the position where the resultant flux. So this is the resultant flux at omega t equal to 30. Because we are adding whatever is a B phase flux to A phase and C phase flux. A phase and C phase flux are only 50% of the peak, whereas B phase flux is 100% of the peak, but in the opposite sense. So this is the resultant flux. Now let us try to see what happens at omega t equal to 90. Let me draw again. This is the A phase axis. This is going to be the B phase axis, and this is going to be the C phase axis. So when I have these three axes, now let us see what happens to the current at this point. A phase is at its peak. So I'm going to have the peak current along this direction. Now, B and C phases at this point, both of them are in the negative side, but that is going to be 50% of the value each. So B negative will be along this direction and C negative will be along this direction. And the total flux is going to be along this direction. So compared to where it was, it has completely moved by 60 degrees. From 30 degrees, it has moved to this horizontal position. So this was, if you may call this as 60-degree position, this is 0-degree position. So it has moved in clockwise direction by 60-degree position. So when the sine wave has traveled from 30 to 90, the flux resultant has also traveled by 60 degrees in clockwise direction. So this is going to be the resultant flux. Whatever we have got here is the resultant flux. Now let us try to look at what happens at omega t equal to 150 degrees. So at omega t equal to 150 degrees, this is what is 150 degree. At this point, A phase as well as B phase are having 50% of the normal or peak current. Whereas at this point, C phase is having the peak value of current, but in the reverse direction. So let me draw this again. This is A phase. This is going to be C phase, and this is going to be B phase. Now, according to this, C phase is having the peak in the reverse direction. So this is going to be the current or flux which is due to the C phase. And we are going to have A phase and B phase both to be positive at this point. So we are going to have A phase as peak divided by 2, B phase also peak divided by 2. So the resultant is going to be along this direction. So this is the resultant. This is the resultant. Okay. So this is going to be the resultant along this direction. Now this is again shifted by another 60 degrees as compared to the previous position. So when the sinusoid has moved from 30 to 90 and 90 to 150, the resultant flux has rotated from plus 60 degrees to 0 degree, from 0 degree to minus 60 degrees. So it has rotated in the same manner, the same kind of displacement as that of our sinusoidal currents that we have applied. So the fact of the matter is, when a three-phase time distributed or time shifted current is applied to a three-phase space distributed winding, a rotating flux, a rotating or revolving flux is created in the inner side of stator cylinder. So the stator is a hollow cylinder. It has windings in the inner periphery, and towards the inner side of the stator cylinder, we are going to create a revolving magnetic field. And the speed of the revolving magnetic field is the same as that of the rotational frequency of the sinusoidal current applied to the stator circuit. So we said that when the sinusoid has traversed from 0 to 30 degree to 90 degree and 90 degree to 150 degree, the rotating flux also moved from 60 degree position to 0 degree position, and from 0 degree position to minus 60 degree position. So we could see that the rotational velocity of the flux is determined by what is the frequency of the applied voltage or current. So if we are having 50 hertz supply, we are going to have 2 pi f is going to be equal to 314 radians per second. 2 pi multiplied by 50. So that is going to be 314 radians per second. So this will be the revolving magnetic field speed. So the magnetic field speed is going to be determined by whatever is the frequency of the applied current or applied voltage. Now, what we are looking at is, if this is the stator, we are creating a revolving magnetic field somewhat like this. So this is the revolving magnetic field we have created, and this is working at 314 radians per second. This is going to be the speed of this particular revolving magnetic field. If we want to express this in RPM, generally you are going to say that 60 multiplied by 314 divided by 2 pi. This is going to be the speed in RPM. So if we are talking about 50 hertz, we are going to get a speed of 3000 RPM. So the revolving magnetic field is really going to work at a very, very high speed. As soon as you turn on the three-phase supply, it is going to create a very high velocity revolving magnetic field. So this revolving magnetic field is as good as having a north pole and south pole physically and rotating this at 3000 rpm. So that is equivalent to that basically. So if I have some winding here, okay, so if I have a copper conductor here, these copper conductors are going to face a continuously changing magnetic field. So they are going to face a d phi by dt. So Faraday's law will definitely come into action here if I put some conductors in the vicinity of this magnetic field. So if I assume that the rotor is here, and the rotor conductors are placed in the outer periphery of the rotor like this, whatever we showed as squirrel cage rotor conductors. If we say these are the rotor conductors, then the rotor conductors are also extending into the board. So you can say the stator is extending into the board like this, and the rotor conductors are also going to extend into the board somewhat like this. So these conductors are stationary and they are going to face this magnetic field. So as the rotor conductors are stationary initially, they are going to visualize a rate of change of flux. So the rate of change of flux is definitely going to cause an induction of EMF. So an EMF will be induced in the rotor conductors, which is proportional to flux, whatever is the flux magnitude, and also the speed. So depending upon the speed, dt is going to be very small if the speed is high, dt will be large if the speed is low. So we are going to see that there is going to be an induced EMF in the rotor conductors depending upon the flux value and the speed value. Now, what we saw was in the squirrel cage rotor especially, we are going to have the rotor conductors short circuited with the help of end ring. So this end ring is going to short circuit this rotor conductor. So because of this, we are going to have actually a current flowing through. So a current starts flowing through the rotor conductors as there is an induced EMF and the rotor conductors are short circuited. If the rotor conductors had not been short circuited, then there would not be any path for the current. But right now, we have short circuited the rotor conductors with the end rings, and we are also having an induced EMF, so there will be a current. Now, this current will produce a rotor flux or rotor magnetic field, which is also revolving, because after all, we are having three-phase conductors. If it is a wound rotor induction motor, we are going to have three-phase conductors. Even if it is a squirrel cage induction motor, we are having rotor bars. So all of them are going to get current from A phase, B phase, and C phase respectively. So this is going to produce a rotor magnetic field, which is also revolving. So let me call this as phi r, and let me call the stator magnetic field as phi s. So we said that the stator magnetic field which is created, we call that as phi s. So we have stator magnetic field phi s and rotor magnetic field phi r. So now there is going to be, there will be an interaction between, phi s and phi r. So that is going to cause a production of torque. So this will produce torque. Electromagnetic torque T. And the electromagnetic torque is the effect of the interaction between phi s and phi r. So the effect will always oppose the cause. So this torque is going to make the rotor, this TE will make the rotor rotate in such a direction that the root cause for torque production will be opposed or nullified. The root cause for torque production is the rotor flux. And the rotor flux was created because of the rotor current. The rotor current is the one which created rotor flux. And the rotor current was due to the induced EMF. And the induced EMF was because the rotor conductors were seeing an alternating or a rate of change of flux. That is the reason why you had an induced EMF. So basically, if we want the rate of change of flux to be not observed by the rotor conductors, the rotor conductor should also start rotating at the same speed as that of the revolving magnetic field speed. So, the rotor conductors start rotating in the same direction as that of the revolving magnetic field of the stator. So if the revolving magnetic field of the stator is rotating in anti-clockwise direction, then the rotor will also start rotating in anti-clockwise direction. So let us say omega s is the speed of the stator revolving magnetic field. Now, rotor will try to catch up such that omega r is equal to omega s. So this will be the goal for the rotor. But the moment it reaches the value of omega s, then there is no relative velocity between the stator revolving magnetic field and rotor conductors. So the rotor conductors will not see any rate of change of flux like what we had been seeing earlier. So there will not be any induced EMF. There will not be any current. If there is no rotor current, there is no rotor flux, then the torque will actually become zero. So if omega L r equal to omega s, then there is no induced EMF in the rotor and no torque. So if there is no electromagnetic torque, then immediately you will see that the rotor speed will come down automatically. If there is no torque, then rotor speed will come down. So if the rotor speed comes down, then again there will be a rate of change of flux visualized, then there will be induced EMF and so on. So ultimately, rotor will settle at a speed omega r, which is less than omega s, such that the difference between these two is good enough to induce a small induced EMF is there in rotor conductors. So we are going to have a small induced EMF in the rotor conductor if omega r and omega s are different by only a very, very small revolutions per minute or radians per second. So we are going to have induced EMF. So there will be a small rotor current and small amount of TE produced or torque produced. So this will be good enough to sustain the rotation against any friction that may be seen because of the coupling between the torque, the shaft and the motor's rotor itself. So we are going to see that if we load the machine more, then you will require more amount of torque. If you require more amount of torque, you will require more amount of induced EMF. You'll require more amount of rotor current. So the speed will come down further and further. So omega S minus omega R, this is generally known as slip speed. That is how much the rotor is slipping behind the stator revolving magnetic field. So this slip speed is going to be proportional to the torque produced or torque demanded by the load. So this is going to be, if you demand more torque, then correspondingly we will require a larger amount of difference between the revolving magnetic field and the rotor speed, so that there will be more amount of induced EMF and there will be more amount of current and there will be more amount of electromagnetic torque produced. So in general, we say that omega s minus omega r divided by omega s, we call this as slip. So it is always measured with respect to omega s. So this is the slip of the induction motor. And this slip is going to play a vital role in deciding how much is the torque produced. How much is the torque produced? So if we have generally higher slip, we will have higher induced EMF, higher rotor current, so higher electromagnetic torque. So as the slip increases, generally you're going to have a larger amount of electromagnetic torque. So if we look at the starting condition of an induction motor, we are going to have omega r equal to 0. Omega s is dependent upon the frequency, which is actually 2 pi f. So we are going to have omega s minus omega r is going to be equal to 2 pi f itself. I may call the stator frequency as f1. So 2 pi f1. This is going to be the stator side frequency. And if you look at the rotor conductors, if this is the stator and revolving magnetic field is in this direction, and if I'm going to have the rotor conductors sitting at the outer periphery of this rotor cylinder, then they are also going to look at the revolving magnetic field during starting condition or under stationary condition. That is going to look as though that is actually omega s itself. Whereas once the rotor starts rotating with some velocity, which is greater than 0, we are going to have omega s minus omega r is going to be less than omega s, because omega r is more than 0. So in which case, the rate of change of flux will diminish. the rate of change of flux visualized by the rotor conductors will diminish or reduce as omega r increases slowly. So as omega r increases, we are going to have omega s minus omega r divided by omega s, which is known as slip. So if I express it in terms of multiplied by 100, this is known as percentage slip. So I can call this as S. So we can say as omega r increases, slip decreases and rotor induced EMF as well as induced EMF frequency, or as well as its frequency comes down. Both come down. Okay. So in general, if I may call the rotor induced EMF under stationary condition as E2, when rotor speed is omega r, the induced EMF will be S times E2. This will be S times E2, where S is the slip. Whatever we have defined as slip, so this is going to depend upon S. And similarly, rotor induced EMF frequency, rotor side frequency is going to be S times F1. So if I try to look at what is F2 or rotor frequency, that is going to be S times F1. The same way, induced EMF in the rotor is going to diminish as the rotor picks up speed more and more. Just to summarize this once again, the principle of operation of the induction motor is somewhat like this. We initially apply a three-phase current, time-shifted current, to the three-phase space distributed conductors of the stator, and that creates a revolving magnetic field in the inner side of the stator cylinder. So this is going to create a revolving magnetic field. Once the revolving magnetic field is created, whose speed is same as that of the frequency of the applied voltage in radians per second. So now the rotor conductors which are sitting inside in the inner periphery, they are going to visualize this as a rate of change of flux. And because there is a rate of change of flux, there will be induced EMF. So that induced EMF will be as per Faraday's law. So as per Faraday's law, you are going to have the induced EMF in the rotor. And the rotor conductors are already short circuited. So you are going to have rotor current. The rotor current is also a three-phase current. So that is going to create its own revolving magnetic field, which is known as phi r. So we are going to have a revolving magnetic field phi r. We are going to have a revolving magnetic field due to stator current, that is phi s. These two are going to interact with each other and they produce an electromagnetic torque. And the electromagnetic torque is going to oppose its own cause. The cause is basically the relative velocity between the revolving magnetic field and the rotor, which is sitting stationarily. So the rotor will try to rotating in the same direction as that of the revolving magnetic field created by the stator. So we are going to have now velocity picked up by the rotor, which is omega r. But once omega R becomes same as omega S, there will not be any rate of change of flux visualized by the rotor. So there will not be any induced EMF, there will not be any torque. So immediately the rotor will try to fall down from its original speed. The moment the speed decreases, immediately there will be induced EMF, there will be rotor current, there will be interaction between stator and rotor fluxes, and there will be a torque. So ultimately, the rotor will settle down at a particular value of rotor speed, omega r, such that there will be a small amount of induced EMF and a small amount of electromagnetic torque produced, which will be able to overcome the friction so that the rotation will be sustained. So, in general, the torque produced is proportional to the product of phi s and phi r. And phi s is a constant. The stator side flux is going to be a constant, but phi r depends upon what is the difference between omega s and omega r. So there is a quantity called slip, which is defined for the induction motor, which is actually defined by omega s minus omega r divided by omega s. And as the slip increases, you are going to have more and more current flowing through the rotor conductors because of higher induced EMF. So if we are loading the motor more and more, there will be more amount of slip. That is the difference between omega S and omega R will increase further and further. So in general, the EMF induced in the rotor as well as the frequency of the induced EMF in the rotor, both of them are going to be proportional to the slip. So slip is a very, very important quantity in the case of a three-phase induction motor. Okay, so slip is defined as omega s minus omega r divided by omega s multiplied by 100. So normally when we analyze the induction motor, we are going to assume that there are two poles only, but the induction motor can be wound for more number of poles. So for example, I can have A here and A dash here, another A1 or something here, and A dash 1 here. So if this is wound somewhat like this, okay, so from here to here itself, the current is completely going to reverse its direction. For example, if this current is coming out of the board like this current is going to go in like this. So this is the way the conductors are going to be connected. And again, we are going to see that this current is coming out of the board like this, whereas this current will be going in like this. So this 90 degrees is corresponding to electrically 180 degrees because this is a positive current, this is the forward current, and this is the reverse current. So mechanical 90 degrees is equal to electrical 180 degrees if there are two pairs of conductors per phase or two poles. So this is what we mean by two-pole winding. So what we need to do is, if we want the conversion between electrical degrees divided by pair of poles, how many pair of poles we have, that will give you mechanical degrees. So mechanically, what is 90 degrees in this case? That is actually corresponding to electrically 180 degrees because this is wound for 4-pole. So this particular case is a 4-pole induction motor. So if I want 6 poles, similarly, I should have A dash, A1 dash, and A2 dash. So if I have 8 poles, I may have A dash, A1 dash, A2 dash, and A3 dash. So similarly, I should have B dash, B1 dash, B2 dash, and B3 dash, and so on. So the more the number of poles, the more complex windings will be, because for corresponding to every pair of pole, we have to have at least a pair of conductors per phase. So that is going to definitely increase the complexity of this entire working. So in general, if I say that omega S is the synchronous speed in electrical radians per second, then I should say omega S divided by P by 2, where P is the number of poles. That will be synchronous speed in mechanical radians per second. And if we want to convert from RPM to radians per second, if we want to convert from RPM to radians per second, so let us say RPM is some ns, and we want to convert that into omega s, we should say 2 pi ns divided by 60. This is what gives me the conversion in RPM. So I should say ns. This is ns equal to 60 multiplied by omega s divided by 2 pi. And after all, we can say omega s is 60 multiplied by 2 pi f divided by 2 pi. So we are going to actually cancel these two. So 60f will give us the speed in terms of RPM if we want to have the electrical revolutions per second. But if we want to actually have it in terms of, so this is essentially in electrical radians per second or electrical revolutions basically. So if we want mechanical RPM or mechanical speed in RPM, we have to divide this by P by 2. So this will be 120 F by P. So the regular expression of 120 F by P is the mechanical speed in revolutions per minute. This is a very, very important expression we use repeatedly. So if we are winding an induction motor for 2-pole 50 Hertz induction motor, we are going to have 120 multiplied by 50 divided by 2. So that will be 3000 RPM. If we are going to have 4-pole, very clearly, we are going to have half of that, which is 1500 RPM. 6-pole, we'll have 1000 RPM as the synchronous speed. And 8-pole, we'll have 750 RPM as the synchronous speed. So omega R has to be slightly less than this. So typical values for a 2-pole induction motor, if I try to look at what is NR or omega R, that is going to be slightly less than 3000, maybe to 2950 RPM or 2900 RPM. Similarly, if I am talking about 4-pole induction motor, speed will be something like 1450 or 1470 RPM. So the difference between the rated speed of the rotor and the synchronous speed is going to be very, very small. So generally rated slip will be anywhere between 1% to 5%, not anything more than that. So the induction motor literally is a constant speed drive. So if I try to plot what is the kind of speed I am going to have for various power output or torque output. When the torque output is literally zero, we will have synchronous speed. And from synchronous speed, it will just drop only very, very little. It is as good as a constant speed drive. So this is the way we are going to have the speed of the induction motor. So the drop in the speed is generally very, very small, even for a large amount of torque production in a three-phase induction motor. Okay. Now, to get the speed torque characteristics of the induction motor, we should know the equivalent circuit. Of an induction motor. So what we are deriving is a per phase, because this is a complete three-phase induction motor, but what we are deriving is a per phase equivalent circuit of a three-phase induction motor. That's what we are trying to derive now. So what we saw in the case of three-phase induction motor, even one-phase cases, if this is going to be my stator winding, A-phase winding, for example, and I am applying VA as the voltage for the A-phase winding, this is going to establish a revolving magnetic field. And if this is the A-phase winding of the rotor, it is going to have an induced EMF. So let us say this is E1, then I'm going to have an induced EMF E2 as per the turns ratio, which is N1 is to N2. And let us say my rotor winding is right now stationary. It is not moving at all. Under this condition, because the rotor is short circuited, I should show it as a short circuit somewhat like this. So this is the representation of the induction motor at only one single phase when the rotor is remaining stationary. So it is as good as a transformer. On the primary side, that is the stator side, you are applying a voltage VA. And on the secondary side or rotor side, there is an induced EMF. And the rotor is short circuited, because of which there is a current flowing. So if I may call this current as I2, I have to call this current as I2 dash when I translate it onto the other side. We all know E1 divided by E2 equal to N2 divided, N1 divided by N2, which should be equal to the other way around. That is I2 divided by I1. This is the way we are going to have the current and voltage relationship. Now, these windings, although they are all made up of copper, we will still have some resistance for the copper winding. Let me show that resistance as R1. And the flux produced by the primary or the stator winding will not completely link with the secondary. The same way, the flux produced by the rotor may not have complete effect on the primary. So some of it will be useless. It is not going to link with the other member. So that leakage flux I'm going to call as a reactance drop. So I'm going to call this as X1, which is the stator leakage reactance. So R1 is stator winding resistance per phase. And X1 is leakage reactance of the stator winding per phase. Now we are going to have the primary winding or the stator winding, where I'm going to have the induced EMF, which is corresponding to E1. So this induced EMF is going to be E1. And what I'm applying here, let me call, instead of calling VA, let me call it as V1. What I'm applying, it could be VA or VB or VC, which per phase parameter I'm considering. So all of them are going to be equivalent voltages because it's a balanced three-phase supply. So V1 is going to be the applied voltage. Now, This is the iron core of this particular induction motor. And I'm going to have the secondary side, which is E2. The secondary side or the rotor winding will also have a resistance, which I can call as R2. And this will also have a leakage reactance, which I'll call as X2. And the rotor is short circuit. So this is how it is going to be. And I can call this as E2. This voltage is going to be E2. And I'm going to have a current which is flowing here, and let me call that as I2, which is the rotor current. So the reflected current on this side, let me call that as I2 dash, which is also equal to I1, hopefully. Okay. Because I'm assuming that the current drawn for creating the flux initially, I am neglecting it. It is very, very small, so I'm going to neglect it. So this is the way it is. So I can again write R2 is rotor winding resistance per phase, and X2 is leakage reactance of the rotor winding per phase. So this is going to be the leakage reactance. Now I can say E1 is induced EMF, self-induced EMF actually in stator, and E2 is induced EMF in the rotor. Okay. Now I2 is going to be rotor current, and I2 dash is the rotor current visualized from stator. So I can write this I1 as I2 dash also. So I can say this is I2 divided by I2 dash. Okay. Now this is when the rotor is not moving. So this is when the rotor is not moving. So when the rotor starts moving, once the rotor starts moving, so we are going to have the speed of the rotor, let us say that is omega r. So we said already slip equal to omega s minus omega r divided by omega s. And this slip is the one which is going to play a vital role in deciding how much is the induced EMF. So once the rotor starts moving, rotor induced EMF reduces to S times E2 from the original E2. So originally it was E2, now it is going to be S times E2. And the rotor frequency, that is the induced EMF frequency, was originally F1. Now it will reduce to S times F1. So we are going to have F2 equal to S times F1. So correspondingly, let's try to draw the equivalent circuit. We are going to have R1, we are going to have X1, and we are having the stator side induced EMF, which is corresponding to E1. So this is going to be E1. And this is the applied voltage V1. So this is going to be the applied voltage V1. And we are going to have this as the secondary side voltage. Now the voltage has become S times E2. That's what we said. The voltage has reduced to S times E2 because the rotor has started rotating. Now we are going to have R2. Now the frequency has also changed. So originally it was F2 and now it has become S times F1. Originally it was F1. Now it has become S times F1. So I should write this as 2 pi F2 times L2. So this is going to be basically 2 pi S times F1 times L2. So this will become S times X2. So you're going to have variation now in the reactance value also. It's not going to be a constant. Now this has to be closed and we are going to have a short circuit coming up here. Now what we get as the current here is still I2, let us say, and the current that is flowing here is I2 dash. So I can write I2 equal to SE2 divided by R2 plus JSX2. This is what is I2, the rotor current. So let me divide the numerator as well as the denominator by S. So I can write I2 equal to E2 divided by R2 by S plus JX2. Okay. Now this E2, what we have got is the same as original rotor induced EMF. What I mean by original is when there is no rotation in the rotor. When the rotor was stationary, at that point, whatever was E2, that is same as this E2 what we have written. So if I say E1 and E2 are basically related, not SE2, only E2. Only E2 are related basically with the turns ratio E1 by E2 equal to N1 by N2. And this is N1 and this is N2. And one more thing we really know is that R1, R2 and SX2 also can be translated to the other side. So I can say R2 dash is rotor winding resistance referred to stator side. So that will be N1 divided by N2 the whole square multiplied by R2. So I can try to take these to the other side. So let me first of all redraw without taking things to the other side. Let me write this is R1, this is X1, and I'm going to have E1 still. And I'm going to have the iron core. Then I'm going to have E2. Then I have R2 divided by S. And I'm going to have X2. Okay. Now this is going to be E1 and this is going to be E2. And this has to be short circuited. So this is the overall equivalent circuit of the induction motor on a per phase basis. Now I want to translate this resistance as well as this inductance to the other side. And I know that E1 by E2 equal to N1 by N2. So I can draw this somewhat like this. So I have R1, I have X1. And what I have as the voltage here is either E1 or E2 dash. Both are one and the same. And I'm going to have here R2 dash by S and I'm going to have here x2 dash. And we will have this whole thing connected together, and this is V1. Now what I have as the current, this current is going to be I2 dash or I1. Either way is fine. So I should be able to write I2 dash or I1 is equal to V1 divided by R1 plus R2 dash by S plus J times X1 plus X2 dash. So I can write this as V1 divided by R1 plus R2 dash by S the whole square plus X1 plus X2 dash the whole square and square root of this. So this is going to be I2 dash or I1. Now, what is actually going into the rotor as the power? If I try to look at it, I should say whatever is the current that is going, I2 square multiplied by R2 by S. So I should say I2 square R2 by S. This is going to be input power to the rotor. So this is the rotor input power per phase. So this is going to be the rotor input power per phase. So I can write this as either I2 dash square R2 dash by S or I2 square R2 by S, because power is invariant whether I look at it from the primary side or secondary side. So this is going to be the per phase rotor input power. Now out of this, the physical resistance is R2. So I2 dash square R2 is going to be the copper loss. So I can say per phase rotor resistance loss. That is going to be I2 square R2. So we can say what is left over as the manifestation of rotational power or mechanical power output. So I should say per phase rotor mechanical power output will be equal to rotor input minus rotor resistance loss. So that is going to be, let us say, rotor output is going to be I2 square R2 divided by S minus I2 square R2. So that will be I2 square R2 multiplied by 1 minus S by S. So all these things are on a per phase basis. Whatever we are looking at is on a per phase basis. So if I want it for all the three phases, I should say total rotor output for all three phases is going to be equal to 3 I2 square R2 multiplied by 1 minus S divided by S. Okay. Now this is the rotor output power, which is supposed to be equal to electromagnetic torque multiplied by rotor speed, TE multiplied by omega R. That is going to be our overall output power. So from here, I should be able to write this as TE equal to 3 I2 square R2 1 minus S divided by S divided by omega R. And after all, we defined omega s minus omega r divided by omega s as slip. This is what is slip. So I should be able to write this as omega s minus omega r equal to s times omega s. Or I can say omega r is equal to 1 minus s times omega s. So let me substitute that from here. So I can write this as 3i2 square r2 multiplied by 1 minus s divided by s, then 1 minus s times omega s. For omega r, I'm substituting this. So I can cancel this and this. So I should be able to write this as 3i2 square r2 divided by s omega s. So this is going to be the expression for torque. So slip really plays a very, very vital role in deciding what is the torque value that is being produced by the induction motor. I already said that I2 square R2 is same as I2 dash square R2 dash. So I can substitute for this 3I2 dash square R2 dash divided by S omega S. We wrote this I2 expression here already. Let me go to that. So this is the I2 expression. If you may recall, we wrote this as the I2 expression. I am going to use this expression. V1 divided by root of R1 plus R2 dash by S the whole square plus X1 plus X2 dash the whole square. So I'm going to write I2 dash is equal to V1 divided by R1 plus R2 dash by S the whole square plus X1 plus X2 dash the whole square root of that. So let me write I2 dash square equal to V1 square divided by this. So if I am substituting this expression here, so I can write this as 3v1 square r2 dash divided by s omega s divided by r1 plus r2 dash divided by s the whole square plus x1 plus x2 dash the whole square. So this is the expression for electromagnetic torque. And I already said that the slip in an induction motor, even under complete rated load condition, so slip generally varies in an induction motor from 0% to 5% or 7%, from no load to full load condition. So whenever I'm talking about even full load condition, I will have a slip of only about 5%, not anything more than that. So if we are considering the slip value to be very close to, so there are two ranges of slip we are going to consider. If slip is close to 0, that is 0 to 5% range. If slip is close to 0, we can say R1 is going to be much less than R2 dash by S, because R2 dash divided by 0.04 or 0.05, it is going to multiply R2 dash by a factor of 20 or 25. So R1 is going to be much lower than R2 dash by S. So this is going to be much smaller than R2 dash by S. Similarly, X1 plus X2 dash is also going to be much less than R2 dash by S. So both of them are going to be much less than R2 dash by S. So I can say TE is approximately equal to 3V1 square R2 dash by S divided by, I can say this is negligible. This is also negligible. So I can simply say R2 dash by S the whole square. Okay. So in that case, of course, I have to have 1 by omega S also, which I have left out. So in this particular case, I will have this cancelled out and I'm going to cancel out the square. So I will have TE is approximately equal to 3V1 square S divided by R2 dash 1 by omega S. So torque is proportional to slip in this particular range when the slip is close to 0. Whereas if slip is close to 1, so that means omega S minus omega R divided by omega S is 1. So that means omega R is close to 0. So when we are starting the induction motor, when it is in standstill condition. So when we are going to have omega R close to 0, omega R is approximately 0. So under that condition, what happens? So we are going to have R1 and R2 dash, both of them being generally very small. The resistance of copper windings are going to be small, but leakage reactance may not be all that negligible. So we will have in this expression R1 plus R2 dash by S is going to be much smaller than X1 plus X2 dash. So because of which I would actually neglect this completely. So in which case I can write this as TE equal to approximately equal to 3V1 square multiplied by R2 dash by S omega S divided by X1 plus X2 dash the whole square. So this is going to be the electromagnetic torque, in which case here we can say TE is inversely proportional to slip. So when we draw these two portions, we can say if these are the axes, this is corresponding to TE and this is corresponding to speed, omega R. And let us say this is the speed, which is the synchronous speed, omega S. And this is the zero speed. So at synchronous speed, slip equal to omega S minus omega R divided by omega S. So this is going to be omega S minus omega S divided by omega S. So this is going to be 0. So slip is going to be 0. So when the speed is omega S, here slip is 0. And this is essentially at omega R equal to omega S. When the rotor speed equal to synchronous speed, slip is 0. At omega R equal to 0, we are going to have slip equal to omega S divided by omega S, which is actually 1. So here is where we are going to have slip equal to 1. So slip is increasing in this direction, whereas rotor speed is increasing in the opposite direction. So initially, we are going to have slip is proportional to torque, and in the other direction, it is going to be a hyperbolic characteristics. So this is when slip is close to 1, and this is slip is close to 0. So these are the two characteristics we are going to have. So we can just draw this in a smooth fashion, somewhat like this. So if this is TE and this is omega R, which is increasing in this direction, and let us say this is omega S and this is omega R equal to 0. So we are going to have something like a linear characteristics, and this is how the induction motor characteristics are drawn. So at some particular point, we are going to have a maximum torque occurring. So this is TE max, or this is the maximum torque an induction motor can generate. If you try to generate a torque more than this, or if you try to load the shaft more than this, the entire system will break down. So TE max is also known as breakdown torque or EBD. So this is the breakdown torque. And this particular slip at which the maximum torque occurs, we call this as slip at maximum torque, ST max. So if you may recall, we wrote the expression for the induction motor torque like this. This is what we wrote as the induction motor torque expression. So let me rewrite this. So induction motor torque is equal to 3V1 square R2 dash divided by S omega S. The whole thing divided by R1 plus R2 dash by S the whole square plus X1 plus X2 dash the whole square. Now to get what is TE max and what is ST max, all we need to do is dTE divided by ds equal to 0. So by solving for dt divided by ds equal to 0, ST max can be obtained. And hence T max or TBD can also be obtained. I'm going to give an approximate expression for ST max. ST max will come out to be R2 dash by X1 plus X2 dash. That is where ST max will occur. And TBD or T max, that is going to be 3V1 square divided by 2 omega S multiplied by X1 plus X2 dash. I would like you to verify these expressions, whether you are getting this correctly or not. But in general, whether we are talking about the slip at maximum torque or whether we are talking about the maximum torque itself, the breakdown torque itself, please note that the frequency plays a very vital role in all these things, because X1 plus X2 dash is going to be 2 pi F L1 plus L2 dash. And this is going to be omega S is going to be dependent upon what is F1, what is the applied frequency. X1 plus X2 dash again here is going to be dependent upon the frequency. So in general, for induction motor torque calculation and speed calculation, the frequency plays extremely a vital role. So this is what I wanted to convey. So what we have seen so far is basic working of an induction motor, its basic speed torque characteristics, and we have also looked at the expression for torque and so on. So induction motor speed torque characteristics is extremely important, and because induction motor had been originally used in Tesla first model of the car, Model X or something, I think it's very, very important to understand how the speed control of an induction motor is done. We cannot say even now induction motor is completely phased out of electric vehicle. So all the more reason we should be not ignoring induction motor. We should definitely try to understand its working